So today we're going to be looking at CPLDs, complex programmable logic devices. As the name suggests, these are inherently complex and not generally covered by hobbyists. They also have the cousins, the FPGA, which stands for Field Programmable Gate Arrays. Now, in the day of microcontrollers becoming so powerful, we seem to have neglected these because they're rather awkward. To program a CPLD or FPGA, you need the correct programming leads, which tend to be very expensive, the actual programmers from the manufacturers. You need to download software environment and tool chains, which are usually 5 to 6 gigabytes download and then 18 or 20 gigabytes space on your hard disk. And they need quite a lot of processing power in order to synthesize and convert your design into a programming file. And the chips themselves are not particularly cheap. And if you're going to include a chip on your own board, your own project, then they also require a lot of circuitry around them to support them. So FPGAs, for example, may require 4 or 5 different power rails. And then you might have separate power rails for your programming voltages as well. So you might even find you to have extra power rails for your programming. However, today we're going to look at CPLD and one specific CPLD, which is the XC9536. This is a 5-volt tolerant CPLD chip. A CPLD chip is non-volatile, which means when we program it, the program stays within the chipset and it doesn't forget it when it powers down. A lot of FPGAs are volatile, which means when you take the power off, they forget the program that you gave them, and then you need a separate chipset, an actual EEPROM, that holds the configuration file, so when it boots up, it then loads that into the FPGA on power up. To show about CPLDs, we're going to be looking at the electronic dice project that I recently did in a previous video, which is basically a 1 to 6 counter and then a switch that allows you to stop the counter, and a very fast A stable that just keeps incrementing the counter, and then the counter will overflow back to 1 when it gets to 6, or technically 7, because it'll be the next count. So, in front of us, we have the same or similar circuit we had earlier. So we have our 7-segment display, our switch with our debounce circuitry here. We have our output of our 3-bit counter, and this is a fast A stable here. Ignore that, we're not using that one. We're using this one over here, which is a variable A stable. I've used a PIC chip basically to do an ADC conversion from a pot into a clock pulse. So we can now use that pot to turn the clock pulse down effectively so we can see what's happening on the chipset. So we can see here that we've got a 1 to 6 counter. There's 6, 1, and then it goes back to 1, so it goes up to 6, and back to 1, etc. And then this bar graph here is showing us our actual bits in the counter. Those of you that are used to binary will know that this counter actually looks backwards because the least significant bit is on the left when it should be on the right. This is because for beginners it's a bit easier to see that counting like so, and that's the same way I did it on my last project. So I want my project videos to be consistent, so that's why it's like so. We need to think about now what happens here. So we have this ongoing counter. We must have an input because obviously you must be able to stop the dice. So in this case, we have the switch that we can press, and then we pause the counter. So you can see the 7-segment display is stopped showing next digits, but the actual counter itself in the chipset is still counting, which is what we had last time, if you remember. We used an enable input on our 4543 chip to freeze the latched display, the 7-segment display, but not stop the counter. So when you pressed it again, it would carry on counting basically from where it left off, etc. Excuse that missed button press there. That's because our clock pulse is so slow, and I've actually synchronized our button press to our clock pulse. So we'll discuss synchronization a bit later, because that's very crucial in CPLD design. You must make sure that you have a synchronous circuit. Last circuit we made, which was the electronic dice project. Sorry, let me just bring it in here. This one was asynchronous, and you can see what I've done is I've taken all these chipsets and I've basically put them into this one chipset up here, which unfortunately is out of focus because I can't get the whole thing in focus. There we go, that's that one up there. So CPLD allows us basically to take a logic circuit and basically program that into its own logic gates. So a CPLD is a purely logic device. It's not like a microcontroller where you've got software running. It actually has physical hardware in it that you set up on your configuration file, and then it basically runs that hardware. So this is purely hardware. This is not software. There's no software in this. The software is only to give the programming file for the configuration of the CPLD. Once you've loaded the configuration file, then this is running in hardware. And that is very, very powerful, because the concept of this running in hardware is that we can create parallel processing, true parallel processing. And we'll discuss that in the next, when we start looking, the next bit when we look at the actual VHDL file, which I've used for this project, which stands for very high speed digital, very high speed design language, sorry, not digital, VHDL. You can also use Verilog, which is another one, but I'm using VHDL. It's up to you which one do you choose to use. There's pros and cons to both. Something else that's interesting as well is that we could put this debouncing circuit into the CPLD as well. We could use several counters and flip-flops to get rid of those extraneous bounces. But as we will see when I look at the software, when we have chipsets which have very small amount of hardware space, we need to make sure we use that as efficiently as possible. And if we can debounce very cheaply on a board or on a project using hardware, which is just a Schmidt trigger and a capacitor and resistor network, then we have to argue whether that's a better use of resources than pushing that onto a CPLD chip, where you're going to waste a number of macro cells. But in big chipsets like FPGAs, which have hundreds of thousands of gates, you wouldn't be too worried about using your debounce circuit in the FPGA, because ultimately it's going to be a very small amount of space you lose, real estate, in terms of the FPGA gates. So let's now switch to the software and have a look at how we do this. So let's start by looking at the datasheets. And this is where CPLDs and FPGAs get it quite complicated, because there's not one datasheet. You'll find there'll be loads of application notes within one datasheet that refers to other datasheets, and you can get lost in various datasheets. But the good thing about the XC9536 is, because it's a very old chipset, it actually has fairly minimal datasheets that you have to look through, so it's a bit more understandable in that terms. We can see that this is for the whole series, so not necessarily our particular one. This is for the whole XC9500 series, but we have between 36 and 288 macro cells, and macro cells, that they are the building blocks of CPLD, so they contain the muxes, the flip-flops, the general logic that you can program to create other things from. So that's really crucial. We'll have a look at a macro cell in a second, but I won't go into it too much. And we've got 36 macro cells in the gate in the chipset we're using today, so we have a fairly small chipset, but you can do a fair amount of it. 5-volt in-system programmable logic. Now this is a problem, because this actually means for our chipset we need 5 volts to program it, and trying to find an old JTAG programmer that is tolerant to 5 volts is very difficult. Nowadays it's 3.3 volts or 1.8 volts, and getting that tolerance is, as I say, tricky. But we got there. I got there eventually. I managed to find a way around it to program it, and there's loads of other discussions here. What is quite good is that you have 24 milliamps drives for IOs, which is just unbelievable. You don't get that these days, to get a chipset that can drive that sort of current. And in and output can be configured to 3.3 or 5 volts. And the beauty of both CPLDs and FPGAs is you can actually power banks of pins separately. So if you wanted, on our case, to have a 5 volt section, we could power one lot of pins at 5 volts. And if you want to have a 3.3 volt section that maybe looks at other chipsets, talks to other chipsets at a lower voltage, you can just power those pins, that bank of pins, at the lower voltage. So you can manipulate the chip quite well when you're looking at this sort of thing. So let's this is all a little bit. So here we have, this is a macro cell here. So we've got 36 of these in the chipset we're using. It looks particularly complicated, so I wouldn't necessarily worry about this too much if you're starting out. Just know this is what's happening. This is what we're trying to build. We're building into macro cells. And then we have global clocks, and global clocks is very important. When you're doing a design, you want to make sure that your clock input goes to the global clock input, because that then makes sure it goes through the macro cells in a very efficient manner. If you put a clock onto a standard I/O pin and then reference that in your design, it may have to route through other macro cells to get to where you want to use it. So it can be very inefficient, and you can have problems with slew and all sorts of other annoyances and skew, which it's just a pain. Just use the global clock pins is the answer. product term allocations, my goodness, and it just carries on. Again, this isn't too bad. And here we go, some outputs. This is quite funny. In-system programmable operation. Sold a device to PCB and program using download cable. This is revolutionary technology here. You'd never believe that you could do this sort of thing these days. Let's have a quick look at our specific one. So we have the XE9536, and we can see that we have 36 macrocells in our one with 800 usable gates. And you just have to be wary about how this all relates, because yeah, you don't necessarily get 800 specific gates you can use individually. It doesn't work that way. We have a high drive 24 milliamp outputs, which is great because we're using LEDs across our whole design to show stuff, so that's very useful. It goes into our connections. Warned you that this is obsolete. It's very obsolete, I do warn you that. We have our supply rails, and then we have our various supply banks that we can look at. So we have the output drivers and then the internal logic buffers. Blah, 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 blah. It just goes on and 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 on. It's not particularly easy to start reading if you want to go through it. There's a lot of numbers and it becomes a little bit complicated. But nonetheless, that is it. All you have to understand is when you're going to build your circuits, you'll build them in macro cells, which are actual physical logic gates. So your device will be physically hardware, not software. And then this is the irony, because you do that through software. And we're going to have a little look. This is the software we're using. It's called ISE. It's a Xilinx program because we have the Xilinx chipsets that Altera do their own, Lattice do another one, and there's a few different big FPGA and CPLD manufacturers. Here we're going to have a look at our VHDL, which is our description language. So that tells us what our chipset is going to how it's going to build our gates into it. You can use schematic entry, and I would really warn you not to do that as a beginner. Some people don't want to see VHDL, they don't want to understand VHDL or Verilog. You can use Verilog, that's another language. And they think, oh, we'll just go to schematic capture and use that. And if you do that, you stand a really good chance of just frustrating yourself, because the first thing you'll try and do is build an asynchronous design because you don't quite understand what you're doing, and then it just spirals and you just end up in a hole chasing your tail. And so just learn VHDL. It's not that difficult. If you've already learned another microcontroller language, then it's very similar, so it's not as difficult as it seems. Before we have a look at our VHDL though, let's first of all have a look at our schematic we looked at last time for our electronic dice. So we have our push button with the bounce circuit. That's still on our board. I showed you that earlier. We do not have our start-stop latch anymore. We're doing that within the CPLD. We do have an A stable on our circuit board, and we are not going to be using this idea of D-type flip-flops made into latches and then make a 3-bit counter out of them, because this is asynchronous design. So we have a clock that goes to one chipset, and then we've got an output from that chipset that goes to the next one, and then the output of that one goes to the next one. So we have a cascade counter technically. So this clock will change. A fraction later, the Q bar will change. A fraction later, C will arrive here. So we then get that changes, and that fraction later that changes, and then that, and blah 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 blah, and you get skew or slew across it, or propagation delay is another word. So the first clock pulse does not arrive at the same point across the whole counter, and that can cause big problems when you start running into high-speed design. So we're going to stop this. We're not going to do this exact system. We're going to create a synchronous counter, so on every clock pulse it just counts up, and then we're going to use another bit of circuitry inside it to create our 4543 BCD to 7 segments. So there's very similar parts to this we're doing it, but we're just doing it a slightly different way. So let's have a look at our VHDL. Ignore our libraries a bit, that gets a bit complicated. Here we go. So we've got our entity dice, and in our first we have our ports, which are defining our inputs and our outputs, and in this case this is our physical inputs and physical outputs. So we have our clock input, we have our enable, which is actually our switch input, we have our 7 seg output, and you can see it's a vector 6 down to 7, so that's 7 actual outputs we're using there. And we have our LED bar, which is 2 down to 0, so that's 3 outputs we're actually using there as well. Then we start architecture of dice. And we're going to start it off by initializing a signal called counter16. And when I had this in my mind, I was thinking 1 to 6 counter, but now it reads as counter 16, which is not what I meant. Sorry, it's a bit confusing. I'm sorry. And that's a standard logic vector again, 2 down to 0. So that's a 3-bit vector, and we're going to preload that. So 0, the 0 bit, which is our lowest significant bit, is going to be 1, and the others are going to be 0. So that starts our counter at 1. So we're going to preload that at 1. We're going to initialize another signal, which we're going to be called enabled, and this is going to keep track of whether or not the switch has been pressed. So this is our first latch. You know, we had our latch on our previous schematic. Let me find it. So this is this latch here. So we're going to use the enabled signal to keep track of what's happening here. And we're also going to preload that to true. If you don't, then the compiler will default it to false when you synthesize. And then we have a initialization flag for the last button press. So we'll go into this in a second a bit more, why you have to keep track of your button press. First of all, first process. So we have when we're doing processes, these are individual areas of sequential logic, which is what is a process in our case. And that has a sensitivity list, which we're going to use clock for. So every time the clock changes, this process will get rerun. And let's have a quick look at it. So if rising edge of clock, then we have to first of all look to see if our counter is already at 6. If it is, then reset it to 1. Oh, I might have told you wrong in the intro, sorry. I think I might have said if it goes to 7. My apologies. So it's if it goes to 6 on our next count, we'll reset to 1. And then I'll tell you why. The reason why I got that wrong is because I suspect, because we're doing an asynchronous design here, yes, we're looking at when it reaches 7 to reset it. We don't have to do that in VHDL. We can just reset it on the next count after we've had 6. And if it's not going to reset, then it's just going to count up. So it's going to add 1 to the counter. And then I've also, at the bottom here, simply assigned counter 616 to the LED bar graph on our breadboard so we can see what the actual counter 16 looks like. The next process we're going to look at again is on the clock, and on the rising edge we're going to see if our switch is pressed. So if our enable equals 1, so our switch has been pressed, so it equals, so that input is high. And we're also going to look at the last button state as well. So we're going to make sure that our last button state, of course, was low, so it hasn't yet gone on a clock pulse. And then we're going to basically, if it's true, make it false. If it's false, make it true, etc. And then load enable into last button state. Now, what this is doing is, because if you held the button down, because it's tied to the clock pulse, you'd end up just keep going through this same piece of logic here, because it keeps registering that the switch presses is been pressed. And we don't want that, because we want one clean switch. No matter how long you hold it, that's only going to be one switch. It's not going to matter how many clock edges has gone since. We just want one clean press. Because if it's a fast running clock, if this is megahertz, then obviously you couldn't press it quick enough to get one clean switch. So we're using this little piece of signal here, this last button state, just so we know if the switch is still pressed from the first time we ran this process. And then obviously, because that will equal 1 if it goes down here, because it gets loaded to enable. So if enable equals 1 here and it equals 1 here, then this then equals 1 and 1, so it won't run this, so it'll just load it there until the switch is released, basically. I hope that makes sense. If you think about it, it does make sense, but I'm not able to explain it quite as well as I hoped I have. And then we have our last process, which again is synchronized on the clock pulse, and this is our 7-segment decoder. And we're also only going to change this output if our enabled is true. So again, that's coming from that first, this is coming from up here. So if our switch press has stopped it, then we're going to change whether we not output the current counter or not. So we're not stopping the counter, that's key here. We're merely disabling the output of the 7-segment from changing. That's exactly what we did in our previous circuit. You remember, we had an enable here for our 7-segment, which we used. We did not stop this from counting. So our counter will still count, and it just decides whether or not it shows us the current count or not. So when we press the switch again, just like our previous circuit, it will show you where the counter currently is, rather than where it would have stopped when you press the switch, because the counter hasn't stopped, it's still counting. It's just that you've frozen the 7-segment display. So that's it. That's all you've got to do. And this is what's interesting, is that all these processes are actually running parallel. Every time there's a clock edge, this process will run as well as this process, as well as this process at the same time. It's digital logic. So it's not like a script where it's running from the top down. Every process is sequential, so they run down this way when it interprets it. But all the processes run together. It's true parallel processing, and this is what's fantastic about CPLDs and FPGAs. You can do things that microcontrollers cannot do. They cannot get proper parallel sequencing. So on top of that, we need to tell it where our inputs and outputs are. So we have a constraint file, and this file just connects the nets that we've used in our program, which is the enable, the clock, the 7 segments, and the LED bars, to the location on the chipset. So pin 5 here, that's going to be a global clock pin. So I would have already looked at that and made sure that is a global clock pin. Again, these don't really matter because they're just general IOs. Now, if you want to be really smart with your design and make sure it fitted in the smallest of space, you'd actually take a lot of time to look at how our inputs and outputs work on our chipset to make sure we don't end up creating huge messes when it comes to driving through our various logic blocks. I haven't worried about it. I've just chosen any old pins for now. And if we have a look at our design, on that one, there should be another one somewhere. That's the one I want. We can see that macrocells used 15 out of 36. So for this small design, we've used 42% of the chipset. Some of that is because we haven't mapped our pins very well, so we could get that better from then. And others of it is merely just the fact that we just have to use what we have to use at the time. But pin mapping is usually another one we can save a lot of space for. Global clocks, look, it's recognised we've used 1 global clock out of 3, so we definitely made sure we're using the proper global clock. And then etc. we've got our inputs and outputs up here. Now, that is pretty much all we need to worry about there. Let's have a little look at what this really means, though, because at the moment this still looks like a programming language, doesn't it? It's still like a script that you might have in a microcontroller. Not so. This shows us how the logic block actually works. This is all the logic gates which our chipset is going to create. So we can see we have the various counters, and within the counters there are more chipsets. So we can see it's going through various inverters and logic gates to build our output. So we've got our 7 seg output, our LED bar output, our enable signal, our counters going through various other gates to get there, or gates and AND gates. So this is entirely logic. This is what it is. It's built entirely from logic. That is the whole point of a CPLD chip, is you're building from your inputs. It's just fantastic. This is just great. You just cannot begin to understand how amazing this really is. The fact that we're building a circuit completely from logic gates, effectively. Well, and muxes and various other things. So that's brilliant. This is what we're designing, and then you basically program that onto your chipset, and hopefully it works well. And if you largely keep the synchronous design, you should be able to easily debug it. So I hope that's been of interest to some people. I admit we've got a very simple design here. We're only using a counter, but we will go on to extend this at a later date. I don't know when just quite yet, but I have a Spartan 6 FPGA, which I need to at some point make a project that allows me to control a large number of servos. So each servo obviously takes a pulse width modulated signal, and we need to produce a large number of PWM signals. The CPLD is too small, unfortunately, to do that, so we have to use an FPGA. We're going to use the Spartan 6, and you should be able to have a look at that and how that's going to change. And the beauty of that, again, is because every PWM we can produce is in parallel, it's separate hardware, completely separate. Every PWM signal can be completely controlled constantly, unlike a microcontroller, which could only update so many, and you could only run so many PWMs from a microcontroller. So we have absolute control, finite control over all these outputs, and there will be inputs as well, but that's one of the major parts of the project. Is it's an automated piece of suit, and I need to make sure all these various servos animate properly to make it look good. And so that's what we're going to do. They're going to create loads of PWM outputs. It's going to be good fun. So you've seen a little bit. I'd highly recommend you have a go and you just have a look at a cheap way of getting into CPLDs, just to experience the technology. It's a different way of thinking. You can do an awful lot with them. And for me personally, the C9536 is one that I started to use when I first got into it, which was donkeys years ago now. So it just shows you how old this was, and they are still really good chipsets, but they're really awkward now to program and really awkward to find the right software to use for them. So Cool Runner is another more up-to-date version, which is still supported by Xilinx, which might be the better way to go, but you're probably looking at a 3.3 volt system. I don't think they are 5 volt tolerant, which is a shame, but it's still manageable. So I hope that's been of interest, and now you've seen two ways of doing an electronic dice project, one through traditional separate chipsets, common chipsets, and then one creating like a master chipset where we've got just a pure logic, programmable logic chipset we've created our own use for and create our own pure logic within it.